Good morning. Welcome to the session on the neuromorphic computing platform within the Human Brain Project eBrain session. I'm Steve Furber, and I'm going to give you an overview of the neuromorphic computing platform. And then my colleague Andrew Rowley will give some introduction to how you use the Spinnaker system and some demonstrations. And Johannes Schemmel will follow up with an introduction and demonstrations on the BrainScales system. Then after the three speakers, we'll have time for some Q&A at the end of the session. So, neuromorphic computing, what is it? Well, within the Human Brain Project, there are two neuromorphic computing platforms that I've mentioned already, the Spinnaker platform and the BrainScales platform. And the platforms that have been offered through the HBP are the first generation systems, and we've also been developing second generation systems. Now, although both of these platforms are neuromorphic computing systems, they are quite different. The Spinnaker system delivers many core simulation, so it's a programmable digital machine with, in the case of the biggest machine, 1 million cores that can be programmed to model neurons, synapses, learning rules, and so on. By way of contrast, the BrainScales system uses analog electronic circuits to emulate the equations that are at work in the biological system. So the emulation is much closer to the biology and how it operates. Both of these systems have in common the fact that they've been designed and built from the transistor up. So they're both based on different forms of custom silicon, and they both deliver neuromorphic computing services at scale. Of course, these aren't the only neuromorphic computing systems in the world. There are many out there, and there's a kind of range of technologies in use. Here I show Spinnaker at one end of the scale, BrainScales at the other. In the middle, there are some familiar platforms such as IBM's True North and Intel's Loihi system. Spinnaker uses programmable digital hardware. True North and Loihi are digital hardware, but highly configurable, but not running software. And BrainScales uses analog techniques. And there are other systems out there at different points on this scale. And there's generally a trade-off. The more you go towards the analog end, the more biologically realistic the electronic models are. And the more you go to the software programmable end, the easier and more conventional the systems are to use. So all of these neuromorphic platforms have unique capabilities and play a role. And the jury is really still out as to which is the best way to build a neuromorphic system, either for modeling biology or for commercial applications. So to offer a bit more detail on the HBP platforms, starting with Spinnaker, this began with the design of a chip, which in fact started well before the beginning of the HBP in about 2006. And it's a chip that embodies 18 ARM processor cores and an industry standard DRAM. And this chip is then packaged, and these packages can be used to tile a two-dimensional surface. The standard Spinnaker board has 48 packages, incorporating 864 ARM cores in total. And these boards can then be assembled into larger machines. And the Human Brain Project service is based on the 1 million core Spinnaker machine at Manchester, which is shown on the right here. In fact, we've been offering a service since March 2016, initially on a 500,000 core machine, and then in November 2018, it was expanded to the full 1 million cores. And this is openly available under the auspices of the HBP, and users run jobs from all over the world. Of course, it's not the only Spinnaker system in existence, and we have been loaning and then selling Spinnaker boards to research labs all around the world for the last 5 or 6 years, and this map gives you an idea of their geographical disposition. The small board, which incorporates 4 packages, is useful for applications such as mobile robotics and for training in the use of Spinnaker. And the 48-node board, the larger board, will support a neural network of the scale of a small insect brain such as Drosophila. In HBP, we've been developing a 2nd generation Spinnaker system. This will incorporate 152 ARM processor cores using more aggressive CMOS technology. And for this, we need larger memories and higher bandwidth interchip links. The key component on the chip is the quad processing element, which incorporates 4 cores in a unit. And this has been physically laid out on silicon and fabricated in small scale Spinnaker 2 prototypes, which are currently in use in the lab. And in the longer time scale, over the next year or so, our collaborators in the design of Spinnaker 2 at TU Dresden will be building Spinnaker 2 out into a data center service called SpinCloud. This is currently outside the Human Brain Project, but this will allow academic and industrial access to very large-scale neuromorphic modeling resources. The Human Brain Project service will continue to be supported on the 1st generation million core machine. And the kinds of things that you can do with this include computational neuroscience, modeling bits of brain, and we'll see some examples of that in the next talk. Testing hypotheses for theoretical neuroscience, trying to work out theories of how the brain works. And also, because Spinnaker is designed as a real-time system, it's applicable in neurorobotics, building spiking neural networks to control robots in real-world applications. The 2nd Human Brain Project neuromorphic computing platform is BrainScales, and this uses the physical model system. So the equations of the biological neuron are re-implemented in analog electronic circuits, which have very similar dynamics. One of the characteristics of electronics is the time constants tend to be much shorter, and therefore BrainScales delivers an accelerated model. Whereas Spinnaker operated in biological real time, BrainScales operates 10 to the 3 to 10 to the 5 times faster than biological real time, which is very useful if you want to, for example, run experiments in long-term learning processes. If you model childhood development, which say takes 5 years on a real-time system, it would take 5 years to run the model. On BrainScales, it may take 5 hours. And BrainScales delivers this technology at scale through the use of whole wafers. So small areas on the wafer implement multiple neuron models and synapse models, and then the whole wafer of these nodes is post-processed to connect them together into a single unit that can be used to support a single neural network. Again, there's a 2nd generation system that's in prototype stage, and here some digital processing is incorporated on chip, effectively using the analog neural modeling system as a co-processor, and the digital system can support learning algorithms running in collaboration and in closed loop with those analog neuromorphic systems. And this allows BrainScales 2 to support hybrid plasticity, doing running alongside the network, measuring the various parameters and working out how to apply learning rules to adjust synaptic weights and other aspects of the network. So that's my 10-minute introduction to the neuromorphic computing platform. I'll be back at the end to answer questions, but at this stage, I'm going to stop sharing my screen and hand the system over to my colleague Andrew Rowley, who will give you some more detail on the Spinnaker setup.
Thank you. I will just start sharing my screen. So yes, I'm going to talk about the various ways to access the machine and give you some examples of what we have done on the machine in the past. So to access SpiNNaker, there's from outside of Manchester anyway, there are a couple of different ways to do that. Basically, we have some local servers next to the SpiNNaker machine that let you access via a couple of mechanisms. One of those is the Human Brain Project Collaboratory, soon to be the eBrains Collaboratory as well. There'll be a slightly different way, but it will look quite similar. And another way that we've been introducing recently is via Jupyter notebooks. So I'll look at these a little bit in detail. To access via the Collaboratory, basically you fill in a form to submit a job. So you select which hardware platform you want. SpiNNaker and the other neuromorphic platforms are on there as well. You then specify what it is you want to run on the machine, so you can write a script, or there are other things that you can do as well. And what happens then is you submit your job to a remote queue system. The queue then holds that, and SpiNNaker's job manager system comes along and extracts the jobs from the queue and runs them on the machine for you. At the end of the run, it then uploads the results back to the Collaboratory, and you can have a look at the results then online. This is a batch processing system, so if lots of people are running jobs at the same time, you might be in a queue. And you're basically emailed at the end of the run, so you know when things are ready for you to look at the results. A second way of accessing this system, as I said, was Jupyter notebooks. So this is a more interactive access. Basically, you type in your scripts and you say run, and it runs on the machine. There is still a potential queue behind the system, but there's more likelihood that you won't be in a queue for this system at this point. This system also allows you to access shared files in the eBrains drive. So if you log on with your eBrains username and password, you can access all your shared files, so you can share files with other people as well. Just a minute, sorry. Okay, apologies. The other part of the Jupyter system is it includes a Neurorobotics service integration. This has basically in the same place that you're running your Jupyter system, we've also added the Neurorobotics platform, and this allows the Neurorobotics platform to then interact directly with the big machine, so you can start running large Neurorobotics jobs on the large machine. To give you details, basically whatever system you're using the Spinnaker software. And the idea of this, as I sort of hinted in the Collaboratory access, is that you write a Pine script and you submit this to the Spinnaker software called SpiNNaker. This interprets your script and passes it down to the software tools that know how to speak to the machine. This converts parameters into the data, and then along with that data and some binaries that we've pre-compiled for the machine, it's loaded onto the machine where it's executed. At the end of the run, the tools then extract the results from the machine, and then these are returned back to your Pine script. So from the Pine script point of view, you're just basically calling run, and you get your results at the end, and then you can interpret them how you like in the Pine script. This is just a Python script, essentially, with some extra interface layers for describing neural networks. So some of the things we've actually done on SpiNNaker, we have run very recently the Cortical microcircuit in real time. This is a 1 millimeter squared area of the cortex, which contains just under 80,000 neurons, 285 million synapses, and it runs in a 0.1 millisecond time step. Now, SpiNNaker was designed to run in 1 millisecond time steps originally, but because the platform is quite flexible, we can program it. And we've managed to come up with a solution that lets us run at 0.1 millisecond time steps in real time as well. So this is quite a success. And we've done some comparisons to check that the results are actually what you would expect to get out of a simulation by comparing with the NEST simulator. And of course, that's been compared against the original measurements in the original paper that this was described in. Some other things we've done, we've also looked at sort of artificial intelligence applications. So this is an example where we've used structural plasticity to train a neural network by presenting it with lots of examples of digits. And then afterwards, we can ask it to recognize digits and select which one it's likely to have selected. So we've shown that this is reasonably accurate on Spinnaker platform as well. We've also run an example of Sudoku problem. So basically where we program it so that you inhibit neurons when things can't happen together. And then we have to add some excitation to this as well to basically make the network run. So we sort of add some random background noise, but everything is otherwise inhibitory. And this is able to sort of solve the Sudoku problem. Now the network doesn't actually know when it solved the Sudoku problem. So sometimes it will solve it and then start again. You can see here an example of the network being run. I'm not sure how well the video comes over, but you can see it's sort of trying to decide which numbers to put in each slot and then coming up with a solution. Another feature of Spinnaker is because it's a programmable system, it's completely, it's ARM cores, so you can program it with standard software. We've actually been able to program virtual environments, which we can then load onto the Spinnaker machine. These can then be loaded along with the neural network and interact on the machine itself. So it means you don't actually have to do any external communication. You can see an example here of the breakout game, which has been played automatically by the machine, trying to maximize its score. Spinnaker is quite good for robotics applications because of the real-time nature of the interaction, and also because we have various external interfaces that allow you to communicate with the machine. So you can see here several examples of robots that we've used in the past, and you can see a sort of animation at the bottom where we're having the pushbot robot follow a flashing light, which it's able to see using a event-based camera. We've also integrated that event-based camera into the Neurorobotics environment now. And you can see there's a pushbot example in here. You can see this is a pushbot basically looking around an environment on the virtual robotics system. This is all running on the Jupyter notebook system with the Neurorobotics platform in the back. And so the advantage here of the event-based camera is you can actually see things actually happening as edges, basically. So you can sort of see the edges of objects as it goes around. So here is an example. It's detecting landmarks, and then it's able to work out where it is in an environment based on those landmarks. So you can see it sort of spinning around here, and every time it passes a landmark, you can sort of see the spikes coming up. And when it's not seeing anything interesting, you don't see any spikes, and that's sort of the exciting part of this. So yeah, there's some examples. I will now pass over to Johannes to do the BrainScales part of the talk. Let me just stop sharing my screen. There we go.
Thank you, Andrew. I will share my screen and will give you a few more details about the BrainScales machine and its integration in the eBrains services in the future. So my name is Johannes Schemmel. I'm from the Heidelberg University, and we lead the BrainScales development together with collaboration partners in Dresden and at the EPFL in Lausanne. So if you use BrainScales, you can access it through the Collaboratory, and it looks like you see a Jupyter notebook. You have a Python-based language to control it, and you have the integration into the Collaboratory and in the future in the eBrain system. But in reality, behind this is a physical model-based emulation of neural networks, which is in reality a bunch of analog electronic circuits. So the membrane traces you see here, they are measured and not calculated. So it feels like a simulator, but in reality, it's an analog emulation. So just to repeat what Steve already told you, how the physical model works. It takes the differential equations for the biology and rebuilds them with electronic circuits. And this leads to a model which much smaller time constants than the biological original. And we use acceleration factors between 1,000 and 100,000. And you see here some measurements from these circuits. So they really look very close to the biological original. And from these circuits, we build up more complex microelectronic chips. Here you see one example where you have hundreds of thousands of synapses here in large arrays, and they all project to neurons sitting here in the center. The neurons, they have synaptic inputs, and then they have leakage and some special terms like adaptation and exponential circuits, so that they can replicate this more complex firing patterns, like the adaptive bursting pattern here to the right. And all this, each neuron has 24 analog parameters you can set to tune the equation so that you can match the behavior of this analog circuit to your biological neuron. And due to the acceleration factor, the model shortens the time you need to do some experiments tremendously. For example, if you want to look into plasticity based learning, which takes hours in an animal model, it takes only seconds if you use the BrainScales system in your laboratory. And if you have complex simulations that do not even reach real time, it is totally infeasible to do this kind of research. And the acceleration factor makes even things like development or maybe even evolution accessible in the laboratory. So the BrainScales system is a multi-level architecture similar to what you have seen in the Spinnaker. It starts with individual chips, and then these chips are aggregated on the silicon wafers. You have seen the picture of Steve showed before, into this kind of electronic modules. And similar to a normal computer system, these electronic modules are put in computer racks and are connected to a central control computer to make them accessible via the internet. But you have to keep in mind that this is still an analog system, so it's a dynamical system that runs in continuous time and solves by its sheer existence automatically the differential equations that are behind the model. And it can scale to trillions of synaptic events per second due to the high acceleration factor. So if you then switch it on and calibrate it, you can tune it to, for example, to represent complex dynamics of large neural assemblies, like in this example after the Brunel paper from 2000. And the BrainScales eBrains services, they will be based on the second generation BrainScales chip, which adds additional learning capabilities to the system we have seen so far. One other difference is that it supports not only the spike-based operation, but also rate-based operation. And the spike-based operation supports structured neurons and nonlinear dendrites, so you can have different kind of spike mechanisms like NMDA plateau potentials or calcium spikes in the dendrite or the sodium spikes in the soma. And this allows you to replicate, here you see some measurements from the system to replicate more complex results from recent biological research, like here the coincidence detection in a large pyramidal neuron, which produces a burst here, the output, if it sees an input at the distal dendrite at the same time than an input at the soma. But simultaneously, you can use the same chip for rate-based modeling, which allows you to do standard machine learning modeling in a very energy efficient and fast manner. Learning and plasticity is the key aspect of this BrainScales system. The idea is that you really use local learning rules implemented within the chips so that you have no communication during learning with the external world and can replicate the biological learning model, the self-sustained learning with local learning rules in the synapses, and test these models in accelerated time to find the correct parameters for the learning to succeed. And therefore, at each synapse in the system, the chip simultaneously measures the timing of the pre and post-synaptic spikes and allows you later to access this measured timing by built-in microprocessor here. And this processor then can calculate the update rules and change the weights, and also it can change the topology by changing some internal addresses for the routing of the spikes. And this allows you to implement structural plasticity. And in addition, for more complex learning rules like three-factor rules or similar things, it can access the voltages and the firing rates and also some modulatory input from other parts of the system. And if you then configure it, for example, to represent this STDP learning rule, it allows you to stabilize, for example, the firing rates here. And you can still use the acceleration factor during this. So a ball time for this here is only 200 milliseconds, even if in real biology it would take 200 seconds to reach this plateau here in the firing rates. This gives you access to new experimental paradigms that have been more or less impossible before, because you can now scan large parameter ranges for plasticity. Here, each dot represents one of these plasticity experiments that take a few hundred seconds in biological real time, but in BrainScales, it can be emulated in just a fraction of a second. And this allows you then to find, you see that the same rule gives you different behavior depending on the parameters you use in the equations. And you see can find the boundary between these different behaviors very easily with this accelerated neuromorphic system. And also, already mentioned by Steve, a very important part is structural plasticity. And here's just an example how this works. You have the fast processor here at the top, and the synapses that measure their correlations, and they are assigned to different presynaptic neurons, here denoted by the yellow numbers. And then you do the experiment, and the synapses evaluate the correlation. Oh, sorry. And you keep just the synapses with the highest correlation, replace the other ones, repeat this. And at the end, you end up only with the synapses that show a high correlation in the plasticity. And you can still replace weakly correlating synapses on a constant basis against random new ones to keep the system adaptive. The structural plasticity can be extended to structured neurons. So you can, for example, make the NMD, change the inputs to the distal dendrites only, or similar things. Here's an experimental example how this then looks like. You can now write in a standard programming language the rules you use. They are executed on the chip in the local microprocessors, and they can use the different sources. For example, here they use the STDP correlation measurements, but they can also use the firing rates here for the homeostatic term of the learning rule. And they then change the weights, and they change the topology here by changing this address. And if you apply this rule, for example, you can learn to recognize these digits in a way that the synapses organize themselves so that they, in the best possible manner, represent the input signals. You see this by the fact that the synapses are now only responsive to the relevant parts of the digits. And you still have the acceleration factor. This whole learning runs in the chip and takes only 1.5 seconds wall time. So hybrid plasticity allows simultaneous rules for structural optimization, homeostatic balance, pre-post correlation, and more, since it's software-based system that is flexible and programmable and has direct access to the analog neurons running in real time in the same chip. So what can we expect then from eBrain's analog neuromorphic computing? We have novel analog modeling capability for neural networks that is highly accelerated, scalable, but this is not yet funded, we must admit. And we have a continuous time dynamics, and know that does not slow down if you add complex structures like structured neurons or active dendrites. Then you can implement local learning with closely coupled SEMD CPU. That means a software-based implementation for your learning algorithm that keeps the flexibility you need to test and try different learning algorithms and parameters of them. And learning also can include the calibration of the analog imperfections. It supports hyperparameter learning because it can freely change all parameters, and it supports structural plasticity and a fully parallel hardware-based measurement of correlations, membrane voltage, and firing rates. And last but not least, the front end the user sees, it's just a Python-based interface you can use via the internet or via the HBP Collab, and it looks very similar to a simulator. And therefore, it also supports all standard analysis tools. So thank you. I give back to Steve.
Okay, well that ends the presentation part of this session. We're quite happy to answer questions if they can be sent in through whatever medium it is that you're observing this on. The session has been recorded, so it will be available for viewing later in perpetuity, I expect. At present, we're not seeing any incoming questions, so we'll give it a minute or two. Do any of the speakers wish to offer anything by way of a summary at the end of this session? They're all staying firmly on mute, so I guess that's a no. Right, well, I think if there are no questions, then we'll wind up the session at this point. I will just put up the, that didn't go well, there it is. Put up the closing slide. Thank you again for your attention, and the Neuromorphic folk have online email technical support streams. Feel free to contact us at any point, and if you wish to use the neuromorphic technology, then there's information in the appropriate place on the Human Brain Project websites that tell you how to apply for access as described earlier. Thank you very much and goodbye.